Hello everyone, welcome to the fourth talk in our lecture series. Today's talk will be given by Srigyan Nandi, and the talk is on representation of topological groups.
Yesterday we started discussing, we started our discussion with the definition of the topological group, and we sought to see some of its elementary yet very interesting properties. So that was the very object that this talk series is centered around. So today we actually go on to look into what representations of topological groups are. Although the definition is quite clear and a bulk of the subject matter will be covered within, I should expect, in the first 5 to 10 minutes. We will particularly look at some of the representations of some standard topological groups, and we will go into seeing the methods that we use to get those representations and classify them. And a lot of this can be extended to other standard groups. So we will be dealing more specifically with the topological groups R, Rn and the circle group. But a lot of these methods can be generalized to C and Cn. So of course, just by we do in the sense that for the theory of finite groups, we consider any arbitrary representation into GLNB, the group of automorphisms of a vector space. Here, since we are bringing the topology in, it will be natural that we cannot deal with just representations, and we seek something along the lines of a continuous representation. And so that is fairly obvious. It will be a topological homomorphism from our group G that we seek to represent to GLNB, and that homomorphism has to be continuous by definition. And this will in fact be what we call the topological representation. So let's just get that clear. So we will be dealing with continuous representations. Right. But the very fact that we had to mention that are representations, which are essentially homomorphisms of groups acting on a vector space V, the very notion that it has to be continuous, it makes us ask one fundamental question, and that is, to define a continuous representation, we must have a topology on the set, on the domain of our homomorphism. Right. So that is to say, we must endow GLB with a topology. And of course, the main goal in our theory is to represent groups over complex vector spaces. So, and since we are dealing with only finite dimensional representation, this will always be isomorphic to some Cn as a vector space over C. And in other cases, we will also represent over real vector spaces. And it is a completely different theory to go outside these two fields. So, essentially, we are asking for topology to be endowed on Cn and Rn. So this boils our problem into a much simpler problem, and we always have the natural topologies on Cn and Rn. So this GLB, and for now I will just take GLB is Cn. So let pi be an isomorphism from GLB to Cn. And of course, to give this isomorphism, we must have a basis of V, and so now when we do, we can take a basis of V given by V1 to Vn, and then we can construct this isomorphism by mapping unique basis elements here to those here. And from this isomorphism, we already know that this has a standard topology. We can pull this topology back to GLB and say that this is the topology. And it's a trivial verification that no matter what basis you choose, the topology is the same. And that essentially goes along the lines of proving that one is finer than the other and the other is finer than this one. So we get the same topology. So that is one problem that we have sorted out immediately. So we don't have to worry about this. So now that we have endowed GLP with the topology, we can go ahead and define what continuous representation will be. So, and it is as you will expect, that is, let G be your topological group. And let B be your finite dimensional vector space. So, as you will guess, a continuous homomorphism from G to this continuous homomorphism from the group to the set of automorphisms is said to be a topological representation. Right. So this is essentially it. So these are the exact precise set of representations that we seek to study and classify. So for a lot of cases, the idea of going through these things will be the same for finite groups, obviously. So we will more so to make things interesting and to in an effort to deviate away from the theory of finite groups, you would rather look at some of these infinite topological groups that we seek to represent. And more precisely, we will deal with R plus, that is, and the circle S1. And today we'll just look at these two, the representations of these two on real and complex vector spaces. So, and a lot of representations of other similar groups, such as R with multiplication or C with addition, their representation will follow similarly from these groups, because this is R. Once you know the representation of R plus and that of R2 plus, I mean, in general, if you know the representation of Rn plus as a group, the representation of Cn plus immediately follows, because with only knowledge of addition and the topology, R and C are basically R2 and C are basically the same. They only differ in the fact that C has a multiplication. So we'll just go ahead and look at R plus. So let phi from R plus to right. So straight out we can get some reductions from this, and that is, if this is a topological homomorphism, then phi of 0 has to be equal to the identity, and phi of S plus P is equal to phi plus E plus I. Right. So before we move into any abstract general vector space, we will first look at one-dimensional vector space. So, and we will spend some significant time on this one-dimensional representation, because using the methods that we generate here, a lot of the higher dimensional representations will be done trivially. Right. So, yeah, here we will go ahead and we will try to we will first try to see our one-dimensional representation of R plus on GL and R itself. So in fact I'll start from here. So we can erase all this. So we seek the one-dimensional representation of R plus on GL and R. So we have that phi of 0 must be 1 and phi of s plus t must be phi of s plus phi of t. So there are some very well-known functions that actually satisfy.
Should be 5s times 5.
Yes, that's the multiplication. Yeah. Yes. So there are some very well-known examples for maps like this. Does anyone have any idea?
The exponential.
Yes, precisely.
So this is GL1R, right?
Yeah, GL1. So for GL1R, we have the exponential terms. So I can very well say e power a, right? For all a belonging to R. And it will in fact be true that these are precisely the only continuous one-dimensional representations of R plus, which we will prove now. Right. So that's basically saying that right, these are the hypotheses of the continuous representation. Then there exists a unique A in R so that ft is e power a. Right? So this is what we seek to prove. So and of course, if this does happen indeed, then what is A? A will be we'll have that f of 1 is equal to e power a, right? So yeah, we'll have that. So how do we go about proving this? So let f be such a number. So let f satisfy our hypothesis. Then what we essentially do is we multiply, we have that f of 1 which can be expressed as some e power a of t. And then you multiply f by the inverse of e power a of t, and we show that that is in fact the unity. So yeah, so with is that Fn is actually e power an, right? Because we have additivity over integers. So if we have f1, we can get that Fn is whatever, and that this will hold for all integers. So for all. And from this, it can again be trivially proved that f of some t by q will be equal to e power a t by q. And this is essentially the thing that we are going to be following for most of these proofs, because once you have proved it for a dense subset, you have that these are continuous representatives and you will extend by continuity. So therefore f of r power, or I would rather say f of t is equal to e power a t for all. So that we have classified all the one-dimensional representations, and to say that we have classified would be wrong because it's just precisely one family of representations. Okay. So yeah. So if we go on and try to extend this,
So I have a question.
yeah.
So here we started with a map from R to R star, but eventually we are proving that it will actually be only the positive reals. It can't be any negatives.
Yes, it will precisely, yeah, that's what will happen because so when you do mapping, actually wait, that should not be right because
Yeah.
if from R to R star, yes, that is in fact what happens because this by continuity it necessitates that the map must be exponential and the exponentiation is only closed for the positives.
And like essentially half of x by 2 and x by 2. Then for any
Right. It will be ft by 2 squared.
yeah, then that should be.
Yeah. So then we can proceed and naturally ask, although this I won't prove now because this will take, it will use another 2 or 3 more lemmas to prove. So we can ask what are the one-dimensional representations of R plus to the vector space C, right? So and you would expect that it is all e power lambda t, where lambda is a complement, and that happens to be the case indeed. But we will, before going all the way there, we will in fact try to represent these groups onto us, or not represent. We'll try to look at some properties of maps from R plus to the circle and then deduce from there that these are in fact, the exponentials are in fact the only possible representation of R plus. So that is in essence, we are just going to study the topological homomorphisms of R plus into the group S1. So that will require a lemma. So a lot of this has actually has to do with some, these are mostly some elementary functional equations. So we give a rule and we allow for continuity and it gives us a unique family of such functions. So we'll be going through a lot of things like this. A lot of the lemmas that we need are involve proofs like this, that where we take a family of functions and the rules are directly derived from the fact that they are homomorphisms and we impose continuity on them to get another family of functions that are precisely those functions that satisfy this. And one of the lemmas is, which I won't prove because it is similar to something that we have done here, which you again break it down into integers and then show that it holds on rationals using density and continuity to extend it. So we take an arbitrary interval minus delta to delta. So this is the rule that we have here. So we are essentially considering homomorphisms, and it would be wrong to say homomorphism because this is not a group, but we are considering additive functions from an interval onto R. So of course, are there any guesses of what the family of functions will look like?
Linear.
Yes, they will precisely be the linear functions. So there exists a unique R belonging to R. And what is this R given by? This R is given by f of delta. So that f t is equal to R, right? And again, again, you can see that the additivity can be imposed. We can break this delta down. So here we won't show it. We won't be able to show it on the rational. But what we will have is, once we have that f of delta is equal to r, we can show that f of delta by 2 plus delta by 2, which is f of delta, that is equal to r, and that is f delta, that is 2 times f delta by 2. So f delta by 2 will be equal to, the way we go about doing this is we will show that f delta by 2 is r by 2, and from this we can go inductively and show that f delta by 2 power n will be equal to r by 2 power n for all n. So if you break it down into powers of 2, those slices on those lines, we have this equality. And then again you can use a rational combination of this. So you get f k times delta by 2 power n is equal to r k by 2 power n for all k belonging to z and k less than 2 power n.
R will be f of delta over delta.
F of delta over yes, slope. R will be f of delta over delta. Yeah. So you break it down into factors of 2 power n, and then you get these rational combinations of 2 power n, and then all you have to do is notice that this set is in fact dense in your interval, and hence f's value follows from continuity, and you can show that it precisely lies in the linear family of functions. So now we can use this to study some homomorphisms onto the circle group. And that is to say, rho r plus right? So this is the claim that we have. Obviously, every row will map our elements into the unit circle, but it will again be given by an exponential now, since we claim that it is a homomorphism. So we can take, so we have the circle here. Basically, what the idea that we're going to use is we're going to use the natural logarithm to pull this b back onto our space. So for that, we'll just consider this open up that is obtained by deleting this point from the image. So let u equal to rho inverse by -1 and precisely this point. So this u is open and it contains 0, right? So there you can find an interval minus delta to delta close contained inside u. So there exists a delta greater than 0. So that is contained inside u. So we can define an f from minus delta to delta to our r, and naturally, since we are pulling this b back, we will define it as the logarithm of rho. So it will take t to log of rho of t, right? So, and this is well defined, since we took our u to be a rho inverse of everything except -1. So we do have a simply connected set. So we can define this branch of the logarithm. So now that we have that, this f, of course, the things I'm not mentioning here, you have to choose a delta small enough such that it is smaller than minus 1 by 4 to 1 by 4. But if you choose that small enough delta, which will necessarily exist, you will have that f satisfies these properties. So you will have that since f satisfies these properties from the last lemma, we obtain that f is indeed a linear function. So for all t belonging to this minus delta theta. And that just uses the standard, I mean, it comes from the very fact that we defined it as the logarithm of this homomorphism rule. So it does satisfy that, and that will basically imply by exponentiating on both sides that rho of t is equal to e power 2 pi I f, and that is equal to e power 2 pi I RT, and I can say that is e power I. So where b is of course the constant 2 pi I. So and since this holds, we have that our homomorphism is indeed an exponential homomorphism. So now we can go ahead and we can try to look at what the representations of these groups look like on GL and GL1C. Yeah. So as I mentioned, it is what it is the most likely thing that we thought it would be. So that is let phi from r plus 2 then
Wait, rho of t is equal to e to the I dt only on t minus delta delta.
Yeah, so-
Then you translate.
yeah.
But when you translate, you will get different values of r for different translates possible.
Yeah,
But
so-
you need to patch it.
Yes, that patching up you can do at those endpoints. So and that essence that in general you are not allowed to patch it up. So there is some detail just that's the reason you select that delta source here, so that the patching up is allowed. So yeah, so and there exists lambda. In fact, this lambda is unique. So that phi of t is equal to e power lambda. Right. So what we do is we take this map phi 1 to, we take this map phi 1 from r plus to r star, right, and we try to obtain it using the information given on phi, and that is we take t being sent to mod of phi 1 t, right. This is again a homomorphism because mod is multiplicative and the group that we are acting it on is the multiplicative group, and obviously mod is a continuous one. So we have this. So phi 1 is in fact a representation of r plus 2 r star, and we have already studied those kinds of representations. So that is to say that phi 1 of t is equal to e power a for some a belonging to r. Right. So we can consider the map phi t to be or rather rho t to be equal to this phi t divided by e power a t. That is to say phi divided by this phi 1. So basically what you are doing is you are dividing phi t divided by mod of phi. So it is a map that will lie on the circle. And again this will be continuous and this will definitely be a homomorphism, since you are just bringing it back, you are just projecting your thing back into the circle. So rho is in fact a homomorphism to your circle. So is topological homomorphism. So you can see the like what we were thinking when we went ahead and tried to understand homomorphism from R class to the circle. Because now when we are going ahead and going to trying to see representations to the complex multiplicative group, what we essentially do is we prove that to any for any such representation we can basically scale it down and project this representation onto the circle to obtain a homomorphism there. And now that we have classified all the homomorphisms from R plus to the circle, we can go back and push it back up and try to use that to classify these homomorphisms that we are interested in. So that is basically, since rho t is a homomorphism from R plus to this circle, we have that rho t is equal to some e power I b, right? And then we have that this map phi t is equal to rho t times e power a. So that is e power I b t e power a t, and that is equal to e power a plus I b times t. So we get that it is in fact equal to e power lambda for some lambda belonging to C. And it is trivial to prove that this lambda is big. So yeah, we have the same exponential family for representations from R plus to the complex number. And what is more interesting is that when you do consider an important family of representations, and that is to say bounded representations, you will have that this real part has to be 0, those representations. So if my representation is bounded, so if phi from R plus to S1 bounded, then the real part of lambda is equal to 0. So that is that. And yeah, so basically for bounded representations, our exponential consists of purely imaginary integers. So then, now that we have done it, now that we have seen these families of representations for R plus, we can go on and actually ask the question for Rn plus. So again, what will follow here is a very trivial application of what we have done. Let phi be homomorphism from Rn plus to C, right? So, okay, of course, what will phi look like? It will be local. What?
Maps from maps to C star.
Because like yes, we already know this.
C star. And I meant to say one-dimensional representations of C that are possible. Alright. So, yeah, a natural extension of this would be to consider homomorphisms from this additive group Rn plus to C star. And what would they look like?
Each component function will be some exponential.
Yes, exactly. So each component function is going to be an exponential. So to each component function, there will be a lambda 1 or lambda 2, lambda 3 and lambda n, so forth. And it will basically go to, yeah, so if we had T1, T2, Tn, that will go to e power lambda 1, T1 plus.
Yeah, it will not come.
Right? So this is basically what we are going to do. And that is a trivial extension because as you said, each component function can be treated as an individual representation. So you notice that what is mainly going on here is not really something special because we are essentially dealing with just functional equations and imposing continuity. So now we can move on. And we can consider arbitrary finite dimensional representations of these groups. So when I say finite dimensional representations, I mean that we are going to try to represent them on GL and C. So for that, we first need something that we might already be familiar with. So let A belong to so for matrices, for n cross n matrices, we can define the matrix exponential. So we define e power a equal to 1 plus a plus a square by 2 factorial plus so on. So this notion of the matrix exponential has already been discussed in some of the previous topics. And in any case, for those who are not there, it has a lot of properties that it shares with the standard exponential map. So, and this is in fact a well-defined map on matrices, and moreover, it maps every matrix in MNR into invertible linear order. So, actually I think we can prove that. So, and we should prove that. So, yeah, let's do that first. So this matrix map, this matrix exponentiation, it gives a very important class of families of homomorphisms. And in fact, we will see that all homomorphisms of all higher dimensional homomorphisms, or to say the finite dimensional representations, will have the form of some matrix exponentiation. And that is a trivial analog of the case for those one-dimensional representations. So our first claim is that this map from R plus to given by t going to some e power a or e power pa, that is e goes to e power pa, is a homomorphism. So the fact that it is a topological homomorphism does not have to be verified because continuity follows trivially. So we just see that it is indeed a representation. So as in it is indeed a homomorphism. So basically we have to show that it respects the group population. So we have pi t times pi s will be e power pa times e power s, right? And that will be equal to I mean, instead of writing the double summation, I'm just directly going to consider the Cauchy product. And that reduces to this summation. So here we just pull a factor of n factorial out to make this expression into a standard binomial expansion, and then the rest follows trivially. So that comes up to be the form that we want. It is s plus p power n k power n by n factorial, and which by definition of the matrix exponential is equal to e power plus s. Okay. So we have that this phi that we define here is indeed topological homomorphism. Phi s plus p is phi s and is hence topological homomorphism. And so actually you can also verify that this matrix exponential sends your operators to invertible operators, since if you have pi of t and you multiply it with pi of minus t, pi of t times pi of minus t. So you do this matrix Cauchy product and you actually end up getting the identity. So each of this map, it takes every matrix into the set of invertible linear matrices. So
an easier way to look at it is that this exponential, this calculation will go through for any matrices x comma y such that we compute xy is equal to yx. PA is equal to x, SA is equal to y. If xy is equal to yx, then e to the x plus y is equal to e to the x.
yes, yes. In fact, that is one of
That is true.
So for commuting matrices, so that is this additive law of the exponentiation doesn't always hold, and it does definitely so when the matrices commute with each other. I think that can be proved from this, right?
Yeah, we just
Yeah.
we've done pretty much.
Yes, alright. So and so now the interesting thing is, these are of course finite dimensional representations of R plus. So, but as before, we asked the question, what else, or are there other finite dimensional representations? So I didn't have the time to do this, but in fact these are solely the only finite dimensional representations, as you would expect. So that is a theorem due to Stone. And if you are interested, you can take a look at it from the book by Balancing matrix groups and representation. I think Lie groups, Lie algebras and representation. So that is the converse also holds. So let phi from R plus to GLN C be topological group homomorphism. So essentially we have to find a matrix such that this map is indeed e power t of that matrix, which we hold to be constant. So what we do is, what Stone says is, if this limit as e goes to 0 of phi t minus identity in a sense, this derivative. If this exists and is equal to this matrix A, then phi t is in fact e power a of t. So these are precise. So not only have we found out the some common examples of representations of the group R plus, we have also been able to give a very simple and neat characterization of all these representations. And you can see how introducing continuity simplifies a lot of things for these representations. So in fact there are a lot of, technically we can go into a lot of weird representations of R plus that are additive, but because of their non-continuity they won't count as topological representation. So we'll see if we can do one, if we have the time to do an example.
I have a question. So, will this limit exist for any topological homomorphism?
Not necessarily.
So, there might be others.
Yes, there. Wait, this limit, I think it should exist.
This limit always exists.
Yeah, this limit
Right.
always exists. That follows from.
To make a trivial phi of t equal to I for all.
Yeah, but
Then it will be
that will
zero.
be
Then the
zero.
limit exists.
Limit
exists.
You get just zero matrix.
Yeah.
Oh, sorry.
Yeah.
If I remember correctly, the limit does exist, but I am not sure which property of phi implies that the limit exists. Yeah, the limit should exist. Yeah, it should, because I mean, this is a heuristic way of saying, but the definition was that the converse also holds for every other homomorphism has to have this one. So I think you should just take a look at the all through where he goes over the Stone's theorem. So yeah. So now this matrix exponential is a bit tricky because you're going to have to compute several powers of these matrices to get what your value of the exponential is. So one way to better understand this matrix exponential is to look at the Jordan decomposition of your matrix. So, and as you may expect, when you understand your exponentiation operation from the lens of the Jordan decomposition, what you get is precisely the matrix exponential is the individual exponential of the Jordan blocks. So, if the Jordan form of A, then e power A is actually S inverse e power j s, and e power j is such that e power j is obviously a block diagonal matrix, and e power j will in fact be the matrix obtained by exponentiating each of the blocks in the block diagram. So that is one way to see how the matrix exponential is acting, and this is going to be fundamental in understanding some other bounded representation of the finite dimension set. So, of course, if A is diagonalizable, that is, if A is diagonalizable, then the Jordan form is precisely a diagonal matrix. With so obviously the diagonals will be the eigenvalues. Then our matrix exponential will, if A is precisely S inverse J S, so J will be equal to this matrix, the diagonal matrix on lambda 1 to lambda n. Then the exponential of J will actually be this matrix e power lambda 1 e power lambda n. Since the exponential on the scalars will coincide with the definition of those for 1 cross 1 matrices. So you get your matrix to be of this form. And similarly, if we look at bounded representation. That is to say, so for the analog for one-dimensional representations it was trivial. If our representation has to be bounded, our lambda is have to be purely imaginary. So a lambda, or to be precise, a lambda has to be purely imaginary. So this is a proof that you can again find in Hall's proof. So there is one messy detail to go over, and in fact it is the same thing as we expect, and that is if these kinds of representations are bounded or of the bounded type, then each of those lambda is are in fact purely imaginary. So in essence the trick is to show that. So obviously if our lambda is are purely imaginary, then we really have that this is bounded. But otherwise, we show that if it is not, I mean, we are supposed to show that if such is not the case, then our image of the exponentials on these functions, it actually turns out to be unbounded. So just as an example, if we take a matrix J to be, we can take a matrix J to be lambda 1, 0, lambda, then e power j will actually have the form e power lambda, no, that is e power ej will have the form this e power, yeah, this is. So you can already see that if our Jordan blocks are not simple, such as those of these kind, we start getting unbounded components on the off-diagonal element. So the general proof is rather simple, that the existence of even one non-zero component of the off-diagonal will start resulting in unbounded component, because now you have this t over here, and that will start going unbounded. So if you consider this matrix as one of those belonging to the Jordan decomposition, you will see that when you take so you will see that the set e power ta, t belonging to R, will in fact turn out to be unbounded. So your only bounded representations of these kinds are those ones in which lambda is imaginary, purely imaginary for all I. So again, this proof is given in Hall's book, and I won't go into the details for this one. So and again, as with the other topological group that we were discussing today, we will look at finite dimensional representations of S1, and we have a similar need for this. Then there exist these integers a in z such that and an invertible matrix S, so that this homomorphism from S1, which is basically again as we expect for the one-dimensional representation case, it was e power IVT for some real t, and it will go in a component-wise fashion. So pi of p will be equal to S inverse IB1 and so component. So this is again easy to prove from the case from this proof. and it will in fact be precisely those individual component wise exponentiations onto the circle. So we have basically covered what we intended to cover, and that is to study the one-dimensional representations and the general finite-dimensional representations of these two groups. So as I said in the beginning, a lot of other topological groups, such as those of C star, can be you can understand their representations from S1, and same with the additive groups of C and I. So, and that was essentially it, because the only new condition that we are imposing on this to get such neat characterizations is the fact that these maps that we define have to be continuous on top of being standard representations. So now, of course, we cannot, there is a lot more to representation theory than just saying that these are homomorphisms. So the entire aim of this series was to in fact dive a bit deep, look at in what one might say small groups, and that is, as you might guess, compact groups, and see what methods that we can use to substitute for things like the averaging trick that we use for the representation theory of finite groups. So I will just end my talk with this, with what we precisely aim to study, and those are compact groups. So again, nothing much needs to be said, but I'll just give some interesting examples of compact groups. So before getting in, a compact group is a topological group that happens to be compact, and we use the same definition of compact, that is, any open cover of the group has a finite circle. So obviously it's not very interesting for the case of finite group. Every finite group is going to be compact, because every finite topological space will be compact. So, and a lot of you might have seen these groups during the talk on matrix groups, so we're just going to revisit them again and not go into too much detail for each other. So, of course, we'll be looking at topological subgroups of the general linear group. So, do you have any examples of compact subgroups of the general linear groups? O(n), U(n), S(o(n), SU, and those are precisely the four groups that we will look at. So, so this is all A belong to GL and R, such that A transpose is wait, wasn't that SON?
No, SON was with determinant 1.
SU is for complex. Yeah,
SO will have
SO is determinant 1.
yeah. So SON is A belonging to ON such that detail is equal to 1. And the same thing for the unitary group. A belonging to GL and C such that, and instead of the transpose here it is the conjugate and the actual conjugate transpose. A star A is equal to N, where A star represents of course the conjugate transpose, and SUN is all these matrices in UN such that determinant A. So any group you take, if since the determinant is a well-defined homomorphism, and you can always take a subgroup of that group where the determinant is equal to 1. So now, these are, how do we actually go about showing that these are compact? So the good thing that we have here is these matrix groups are again, we endow them with the Euclidean topology. So it suffices to show that these matrices are in fact bounded and closed. So ON is definitely bounded, because forget this definition. This essentially says that the rows of ON are orthogonal to each other, and moreover they are orthonormal. So if your rows, so if your rows are orthonormal, that means each of them have length 1. So since the condition that the length of your row is 1 already gives a bound on how large your each individual entry can be. So is bounded, and for that reason this is bounded. Un is also bounded because you are basically telling on the complex inner product space you have modulus 1. So bounded, bounded. So what are we left to show? We are left to show closure, and closure is a very easy property to verify because if you have a sequence of matrices in OM that does converge to another matrix, you have that in OM that each of these rows are orthogonal to each other. So that orthogonality is basically a polynomial property that can be expressed as a polynomial relation, and hence the sequence to which it converges will also have the orthogonality of rows, and therefore it will be closed. And again, when we take determinant A is equal to 1, determinant is a homomorphism, and when we say determinant A is equal to 1 is a closed subset of R, a singleton. So we are taking the inverse. So this is in fact a closed normal circle of OM. So again, closed, bounded, closed, bounded, closed. So these are all your prototypical examples of compact matrix groups contained in GLNC and GLNR. And in fact, mostly these are the groups we study. And we aim to, it helps to kind of, in a sense, visualize what is going on here. So I'll just quickly go over the topology of these groups and then leave with it. So when we take OM, let's take, we know for O2, so we can consider O2. Right. So O2, we know that, what does the standard element of O2 look like?
Cos theta sin theta minus.
Exactly, it is the Jacobi rotation relation, right? So, but for O2, you have two kinds of rotations. Those rotations which preserve orientation and those rotations which just
Reflection.
flip. And so it's very similar to what the dihedral group does. So you have rotations and you have flip rotations. So, yeah. So, yeah, so for all real theta, instead of going real, I can just say for all theta that lies in this, I can define R of theta to be for those rotations that preserve orientation and change angle by theta. So that will be cos theta sin theta minus sin theta cos theta. So using this, we can I'll actually define this to be what's the determinant for these? These are determinant one. In fact, these are precisely the elements of SO.
Yes.
So this is SO, right? So I can define isomorphism S1 to SO2, where e power I theta is sent to R theta, right? So SO2 is actually the circle. It's a matrix group, but more importantly, it is the circle. Now, what do the remaining elements of O2 look like? Those are precisely these. They look like these ones, except that they
into a transversal
reflection.
exactly. So how do we get them? So essentially, any element of O2 will have one of the rows like this because it has to be orthonormal. So the other one would have either been plus this, which is minus sin theta cos theta, or minus this. So basically, you get that is this thing times something that negates
1 0 0 minus 1.
Yeah. So what will that be?
1 0 0 minus 1.
1 0 0
Yes.
Theta times this 1 0 0 minus. Yeah. Right. It is this. So again, so you have just parameterized it by this matrix 1 0 0 minus 1, which you could say, let us say it is some A. So R theta times A. So you have O2 is precisely the disjoint union of this along with this. And similarly, since this is parameterized only by constant A, we can again construct a topological isomorphism pi S1 to this thing. So O2 is basically, topologically speaking, it is the disjoint union of two circles. O2 is the space consisting of the disjoint union of two circles, and SO2 is the space consisting of one of those two circles. So then finally end this with a similar description of U1. In fact, you can actually go ahead and prove that O2 is in fact, I think O2 is in fact the semi-direct product of S1 and SO2, I think, because that's what it's coming to be. I'm not sure. You should go and verify. So, because these kind of maps tend to increase semi-direct product, so it should be the
So
semi-direct.
2 with plus minus 1, is that right? You are writing a 2 images, so probably so 2 with plus minus 1.
Yeah, S1 with plus minus 1, right?
S1.
Yeah, same thing. So 2 with plus minus 1. Yeah, that should be the, or at least the group theoretic breakdown of O2. So now we will finally end with U2. How do we construct general elements of U2? So for at least for O2, we could start out with one vector with modulus 1, and then we had to find the corresponding row that preserves those orthogonality. So for U2, we can start with some AB belonging to C, such that again the modulus is 1. So such that mod A square plus mod B square is equal to 1. So then we have these kind of matrices R A B given by A B B conjugate. So these are in fact elements of U2, and by taking the determinant A conjugate mod A square plus B conjugate, that gives 1. So these are in fact elements of SU, right? So, and on top of that, you can even verify that simply because these kind of elements, they are in fact closed under matrix multiplication. So ABCD will give another matrix of this parametric form. So you get that this actually forms a subgroup of SU. We are not yet sure if this is indeed SU. Yes, this is SU.
Yeah.
But from this we can only say that fine. We will eventually prove that this is in fact SU. Moreover, since we have been able to give it into a linear parametric form, it will in fact not only be closed under multiplication, it as a topological group will be closed in its own right, topologically. So we can in fact, and moreover, since U2 is bounded, we have that this thing. So this subgroup of SU2, which is basically, you can parameterize it by this order as. So what is this? Is it AB belonging to C2, which can be thought of as R4 again, because you do a component wise split, and these are AB such that mod A whole square plus mod B whole square is equal to 1. So you can see that when extended and visualized as a subspace of R4, this subgroup of SU2 is basically the sphere S3 embedded in the 4-dimensional space R4. So in fact, that what more than what we intended to prove, what we intended to see that this can be visualized as S3. We have proved a very nice result that S3 in the 4-dimensional space R4 is actually a group, and this is not a property that a lot of circles share in n-dimensional space. So S3 in R4 is a group, right? So S3 can in fact be made into a compact topological group in R4. So now, since I won't do that, but yeah, whatever he said, this you can trivially prove to be in fact the group SU2. So now I will go back and I'll ask the same question that I asked for O2. So if I start with matrix in U2 and I say AB, what are all the options that I can think of for the other remaining column of this thing? It must be parameterized by some e power I theta. So again, I'll use that rule. I think it is e power I theta or e power minus I theta. No, yeah, it's e power I theta. So we had a b minus b conjugate, a conjugate, so we get minus e power I theta, b conjugate, e power I theta, a conjugate. I think this is it. And now this theta can be parameterized for any angle from 0 to 1. So in fact all matrices in U2 can be parameterized by some f a comma b comma theta. And you will see that since we have a spectrum of theta over here, U2 is actually going to be S3 cross whatever space can parameterize this theta, which is S1, with the product of it. And in fact, again, these maps, they should give that U2 is the semi-direct product of S3 and S1. So you get one visualization of U2, which is S3 cross S1, and SU2 is the special unitary group. It's precisely the sphere S3, which is crossed with one of the elements, and that is e power I theta for which is when it is 1. So this is a visualization of some of the more common compact topological groups that you will encounter with the finite element. And yeah, I think I'll end with this. So from the next time, we'll actually see how some relevant substitution for the average ring can be put on the compact groups by using the notion of a R-ring. And then we can actually study further things in the representation theory that may take more importance, such as Schu's lemma, character K. That's it.
Thank you so much. Are there any questions?